good morning or afternoon or evening, whatever it is for you. I'm just being in the classroom with you still. I have a makeshift smart board that we created this weekend from Staple Supplies. We're going to try to make this work the best that we can. This week on Monday and Wednesday, you're going to get new notes. You're learning new material. We're going to try to keep the video short, and then on Flipgrid there are some practice problems that you can try out, as many as you need to, so that you can get really good at each topic. Today's goal is that you begin to understand how different parts of an exponential function impact the graph, that you can identify growth and decay factors and rates, and that you can apply growth and decay equations. So hopefully you had a chance to print out the notes so you can follow along. Let's get started. So exponential growth and decay, you looked at those two examples, the paper folding, the graph grew slowly at first and then very quickly, and decay, your mammoth started off dying little bits and then gradually they went extinct. An exponential function is a function that's in the form of y equals a parentheses b to the x power. So now our x is our exponent. Exponential functions are non-linear. When you graph these, when you graphed your paper folding and your mammoth activity, you did not get a line, so that makes them non-linear. There are 5 different exponential functions that you're going to go to desmos.com, use this link, and you're going to graph and sketch the graph of each of these functions. You can pause the video. I'm going to keep going on as if you've already done that. When you're typing, there are some directions here for how to get the x to be your power. When you graph this one, you should have noticed, things to notice, is that this number here was your y-intercept. So for this graph, it crossed y at 2. And this number here tells you if it grows, if it goes up, or if it decays, it goes down. This number is greater than 1, so it was going up. The other thing that you should notice is that it never actually touches the x-axis. It gets very close to it, but never touches it, because we never get 0 when we put in, if you put in a negative number here, you would get a very small decimal number. You would never get something that was below 0. So this graph is going to stay in these 2 quadrants. It's not going to go to quadrant 3 or quadrant 4. Let's go. For this one, you should have noticed that it crossed the y-axis at 3. That's our y-intercept right here. And then again, it went up from left to right. And again, this was a graph that stayed. Don't go by mine because I have no, it's just like being in the classroom. I have no grid marks that I can see. It should cross at 3, and then it goes up from left to right. And again, it doesn't touch the x-axis. It gets very close to it, but doesn't touch it. This one was different because it should have crossed y at 2, but then because this number is less than 1, this graph was going to go down in this direction. Again, not touching the x-axis, but it gets very close to the x-axis. This number, this one should cross at 3 and go down from left to right. And all of these graphs right here are staying in these first and second quadrants. The only one that didn't stay in the first and second quadrant is this last one. This last one looks very similar to the first one that you graphed, except for my y-intercept is negative. If your y-intercept is negative, it's going to reflect, is going to be a reflection of the one where the y-intercept was positive. So if you can imagine, this and this just flipped. So this one will never go into quadrant 1 and 2. It will stay in quadrants 3 and 4. Okay, so exponential functions have that line that they get very close to, but they never touch. And in math, we call that line an asymptote. So an asymptotes are either a horizontal, a vertical, or a slanted line that your graphs will get very close to but not touch. That's all you need to know about it right now, is that that's what it's called. You'll learn more about that in later math classes. When a quantity grows exponentially, it increases by the same percentage over equal time periods, and that's exponential growth. When a quantity decays exponentially, it decreases by the same percentage over equal time periods, and that's called exponential decay. Scroll up. Up. Scroll the other way. The formula for exponential growth and exponential decay is y equals a, and then in parentheses for growth, it's 1 plus the rate of growth. And I'm going to use t instead of x for the time period, but that could easily be an x. But I want you to remember that's each time period. A in math is our y-intercept. This whole thing together is called our growth factor. It's what we are multiplying by each time. So if you think about the paper folding, each number of rectangles kept multiplying by 2. You had a growth factor of 2. The rate was, it was doubling each time. The rate, it was changing by, it started off as 1 rectangle, went to 2 rectangles. It added 1 whole rectangle, which is 100% of itself at that time. So its rate was 100%. Exponential decay is y equals a 1, but instead of adding the rate, we're going to subtract the rate over each time period. Again, the whole parentheses is called your growth factor. A is always going to be our starting number, our y-intercept. So for the paper folding, you started at 1 rectangle. Then it doubled. It grew 100% each time. The growth rate was 100%. Rates are generally given to us as a percentage, but we're going to change the percentages to decimals in order to work with them in the equation. So you want to be able to recognize, looking at an equation, is an example of growth or decay. And to do that, you're going to look at the number that's in parentheses. This number in parentheses, 1.5, tells me that it is a growth because it's greater than 1. So anytime what is in parentheses, or our b number, remember y equals ab to the x power. If b is greater than 1, it's growth. If b is less than 1, then it's decay. The rate is what was added to the number 1 to get it to be what it now is in parentheses. So this parentheses, this 1.5 equals 1 plus whatever the rate was. So you would have to add 0.5 to 1 to get it to be 1.5. And I'm going to change the rate to a percentage when I'm asked what the rate is. So the rate would be 50%. The factor is the whole parentheses. The factor is easy to figure out. That's what it's being multiplied by every single time as it moves along the x-axis, 1.5. Here, this number is less than 1, so I know it's decay. Now I need to figure out my rate. So 1 minus my rate had to give me that 0.75 that you get in parentheses. So you would have to subtract 0.25 And now I want to write my rate as a percentage, so I would say it was 25%. That's how much it's decaying each time period. My factor is the whole parentheses, which is 0.75. For the final one, my number inside parentheses is greater than 1, so I know it is growth. My rate is 1 plus what would give me 2, and that would be 1, but I'm going to change it to a percentage. So that's 100%. If something increases by 100% of itself each time, that means it's doubling. The growth factor is 2. Now going on to some examples of when you'll see growth and decay. This first example, a dish has 212 bacteria in it, and the population of bacteria will grow 80% every 2 days. So the important things for us to be able to write our equation are our starting number. That's our y-intercept. So we're using the formula y equals abx, or for growth, it's going to be y equals a, 1 plus the rate for each time period. So my equation here would start off y equals 212, and then my parentheses is going to be 1 plus, now I'm looking for my rate. My rate is 80%. So it's 1 plus 80%, but we can't add percentages, we need to make that a decimal. So we get 1.8 in parentheses to the x power. This is the equation that you would write based on this information. My rate is 80%. The factor is the number that ended up in the parentheses, and that's 1.8. Now I want to be able to use it to figure out how much bacteria will be at each day. So this one says, how many bacteria will there be at 4 days? I know that this is happening, each x represents 2 days. So if I want to know what it is in 4 days, I want to use a calculator. I want to plug this in. And my x, if each x represents 2 days, and I want to know what it is at 4 days, I want to know what it would be when x is 2. If you do this on a calculator and you want to do the exponent part first, unless you have a calculator where you can type everything in, and the Desmos one will let you do that, you would type in 212 parentheses 1.8 parentheses raised to the second power. If you do that, then you should get 687, and I'm going to round to whole numbers just to make learning at home easier. Now for this one, I'm going to type in that whole thing again, but now my power is going to change. If I want to know what it is at 8 days, and this happens every 2 days, I want my power to be 4, because in 8 days, there's 4 sets of 2. And if you plug that in correctly, you should get 2,225 if you round it. And for the final one, where it's 11, we're going to have to plug in 5.5 for the exponent, and you should get 5,374. I'm going to erase this so we can go on to example 2. Okay, so for example 2, we're looking for our rate, and we're also looking for our y-intercept. So this is termites on a porch. They're 800,000, so that's definitely going to be our y-intercept. That's our A, our starting number. Now I want to decide, is this growing or decaying, this situation? And it says it would kill 40% of the termites every day. So that's our time period, and that's our rate. It's definitely decay because it's killing. So I want to do 1 minus 40%, which would give me 0.6 in the parentheses, x. The rate is 40%. and the factor is 0.6. So now on a calculator you would plug in 800,000 parentheses 0.6, and for 3 days, if this happens every day, we're just going to put a 3 in. And if you put a 3 in for that, and you round it to a whole number, you should get 172,800. That's how many termites will be left after 3 days. For this one, we're going to plug in the equation for our exponent. If it's 36 hours, that would be a day and a half. So we're going to put 1.5 in as the exponent. And if you do that, you should get 371,806. So after a day and a half, it would be down to 371,806. And for the last one, for 2 weeks, if this happens every day, we want to put 14 in for X. Then we're going to get 627. And then our final example, can you raise that up? In June, a 5th grade class started out with 10 mealworms. Raise that up, hon. Nope. Oh, you can't go up any further. All right. For an experiment, the population of worms will double grow by 100%, so there's our rate, every month, and that's the time period. So we're starting with 10 mealworms. If it's growing at 100%, that's 1 plus 1 would give us 2 in the parentheses to the x power. Something that grows at 100% actually doubles. That's the factor. So for 3 months, we're going to do 10 parentheses 2, and we're going to put a 3 in as our variable. And you should have for that one, you should get 80. For a year, that would be 12 months. So we're going to do 10 parentheses 2, and the power is going to be 12, and you should get 40,960. And then our very last one, 45 days, we're going to treat every month like it's 30 days, so that would be a month and a half. So we're going to do 10 parentheses 2 to the 1.5 power. And you should have 28. Now you can go to Flipgrid and watch some videos that you think you need more support on, and let me know.